Okay.
Okay, greetings everyone, and thanks for joining today's edition of our division seminar series. Today we have Dr. Matthieu Hénaff, who will be speaking to us about the use of coastal altimetry to improve meridional overturning circulation estimates in the South Atlantic. A brief intro about Dr. Hénaff. He received his PhD from the Université Paul Sabatier in Toulouse, France in 2008. And he's been a civil scientist since 2015. Okay, I think Matthieu, you may start.
Thank you, Kandaga. So my presentation today will be about coastal altimetry to improve the MOC in the South Atlantic. I would like to acknowledge my co-authors from EOML, Marion Cassale, who actually did many of the diagnostics I'm going to present today, as well as Chris Minen and Annelise Perez, and many collaborators from various labs in South America, South Africa, and Europe who shared their data in situ and satellite data with us. So this study is motivated by the MOC estimation, which, as many of you know, is a crucial component of the climate system. In the North Atlantic, it's the region of deepwater formation, and in the South Atlantic, it's the nexus for water masses that are formed remotely either in the Indian and Pacific Oceans, as well as Antarctic bottom waters, and also the North Atlantic deepwater coming from the north. And it's also the only basin where heat is transported equatorward and not poleward. And so there are two main observing systems in the Atlantic, one in the North Atlantic, that's the Rapid MOCA array that has been deployed since 2004, and in the South Atlantic is the MOC basin-wide array called SAMBA at 34.5 degrees south since 2009. And so focusing on that southern array, the SAMBA array is mostly composed of pressure-equipped inverted echo sounders, also known as PIs, that are mode instruments that measure the travel time between the surface and the bottom. And thanks to lookup tables, we can derive the vertical thermohaline structure from that. And they also have a bottom pressure sensor. And so the map shows the locations of the moorings on each side of the 34.5 degrees south line. And in between two of the PI's moorings, we can, thanks to the vertical thermohaline structure derived at two consecutive moorings, we can estimate the geostrophic current integrated between both, and to estimate the geostrophic current anomaly. And so using this array, the MOC transport recent estimates are of around 17 Sverdrup with about 15 Sverdrup temporal standard deviation, and that's the work from Marion in the past couple of years. And so if we zoom in on the boundaries, so here is along the South American coast, we see one of the limitations of the SAMBA array is that the most inshore moorings are about at the 1300 meter isobath, and there is no continuous measurements inshore of that mooring. And so currently the transport that is inshore of those moorings is estimated using model simulations, and that transport can represent up to 3 to 4 Sverdrup depending on the estimates, and that's about 20% of the MOC potentially that is estimated without direct observations. And so that's the motivation of these studies, to use coastal altimetry data to fill the gap between the most inshore moorings and the coast, and that's a project that is supported by the NASA Physical Oceanography program. So the methodology and data that we propose to use is to use along track data along the reference Topex Poseidon Jason series. So those satellite tracks are in magenta on the figure, and we want to use track 254 on the west along South America, and track 209 in the east along South Africa, that are both in red in the maps. And first we're going to focus on the JSON2 data series, which is between 2008 and 2015, because it's the longest overlap with the SAMBA array so far. And using this altimetry data, we derived the sea level anomaly, from which we can then derive the geostrophic current, which by construction is perpendicular to the satellite track, and which will allow us to estimate the current that is crossing this line between the mooring and the coast. And we also use in situ observations to estimate the structure of the current on the shelf and in the shelf break, to estimate if those components, how much barotropic or baroclinic they are, in order to be able to integrate the surface geostrophic current on the vertical and be able to estimate the geostrophic transport. And in order to access the mean component of that transport of that geostrophic current, we need to use a mean geostrophic topography, the mean dynamic topography, or model outputs if the MDT available are not reliable. And the geostrophic component is the Ekman transport, which is going to be estimated from atmospheric products. So the altimetry data that we are going to use are coastal altimetry data, and there are several data centers that distribute this type of data. There's the Center of Topography of the Oceans and the Hydrosphere, CTOH, in Toulouse, France. There is the Pistache, now Peachy, products developed by CLS in Toulouse, also in France. And there's the ALES retractor data developed by Marcello Passaro and Christian Schwadke at DUT in Germany. And the advantages of using coastal altimetry is that the data extend closer to the coast than standard Aviso data. They are also available in high frequency, which allows a higher spatial resolution. And also the data treatment is improved compared to standard data with improved retracking methods or improved geophysical corrections that allow better quality data up to the coast. We also, when it comes to the pies moorings, we can derive the sea level anomaly from the pies moorings by using both the bottom pressure and the density profile estimated from the travel time. With the first one, we can derive the barotropic component of the sea level, and with the second one, the baroclinic component, and the sum of both gives us the total dynamic height anomaly, which is comparable with the satellite sea level anomaly. So that we first perform the data evaluation along South America by comparing the altimetry derived sea level anomaly and the dynamic height anomaly at mooring A, which is the one circled on the map. And so we first looked at CTOH data, and we found a correlation between both data sets close to 0.5. And when we looked at the Peachy data from CLS, the correlation was slightly higher, but very close. But the root mean square error is slightly larger for those Peachy data and lower for the CTOH data. And we also see that both data sets include the lowest values and the higher values of internal variability that is present in the in situ observations, and both anomalies are found in the satellite observations. And we also estimated the root mean square difference between both data sets, and it's much smaller than the root mean square error estimated between each data set and the in situ observations, and that suggests that most of the errors are shared between both satellite altimetry data sets. We then estimated the geostrophic current anomalies from these along track data, and this figure shows the time evolution on the x-axis, and on the y-axis is the latitude, and the color code shows the amplitude of the current anomaly in centimeter per second. And first, so the dashed line represents the latitude of the Samba array. And south of it, we see that where most of the variability is associated with the Brazil current, and the signature seems to be more intense in the Peachy data. North of this latitude, the CTOH data extend closer to the coast that you can see here. And we also notice south of this band, there's a band of positive anomaly around 34 degrees south in the Peachy data in the bottom panel around here. That the reason for it is not very clear, but it looks spurious. And we estimated the root mean square difference between both data sets, and it's around 12 centimeters per second, which is comparable to the RMSE estimated in other coastal regions. And so from now on, we're going to use the CTOH data for subsequent analysis because we found them slightly better than the Peachy ones. So now, how can we estimate the geostrophic transport from this altimetry? Because altimetry just provides surface data. So we need to estimate the vertical structure of the current. And for that, we use available in situ data. So we have access to the pies moorings on each side of the 34.5 array, but we also on the west have access to lowered ADCP sections, and on the east to 3 moored ADCP that are located on the shelf break. So focusing on South America first, so we have had access to 45 lowered ADCP profiles inshore of mooring A. So those are the crosses here on this map. So mooring A is the most inshore mooring from the Samba array, and you see all the crosses in between that came from cruises to deploy the Samba array that took those measurements. And so we first separated those data into 3 zones. One that is in the upper shelf at depth shallower than 70 meters, then an intermediate zone between 70 and 400 meters, and then a deeper one further down the shelf break beyond 400 meter isobath. So we then rotated the velocities into alongshore and cross-shore directions, and we picked the angle of the roughly the 400 meter isobath, so that's 32-degree rotation, in order to estimate the structure of the current. And we then followed the same approach as Lago et al., who studied current data on the shelf just south of the Rio del Plata, which is a few degrees south of this region in the North Argentine continental shelf. So they examined the currents, but under the surface Ekman layer, which in our region is estimated to be 35 meter deep. And then they estimated the barotropic current as the average current on the vertical, and they estimated the baroclinic current as the total current minus the barotropic component. And then they performed an EOF analysis of the velocity field. So first we looked at the structure. The current rose from all the available LEDCP data, and we see that the current is mainly southwestward and following the alongshore direction along the 32-degree axis, and that's the signature of the Brazil current. There is a small contribution of the currents in the cross-shore direction, but since it's really dominated by the main alongshore current, the cross-shore component will be neglected in the subsequent analysis. If we looked in the 3 zones, the average current on the vertical and the shallower area in zone 1, we found very little shear on the vertical, and the shear was more pronounced in the other 2 zones. But then we realized that those variations are also largely due to the fact that not all profiles go to the same depth, and so that kind of affected our analysis. And so we realized that we had to split the zones 2 and 3 in 2 separate subzones in order to have profiles that go to equivalent depth. And so we ended up with 5 zones as presented here. And we performed an EOF decomposition of the alongshore current in these 5 subzones. So in black is so those are the vertical structure of the EOF 1 and 2. And so EOF 1 is found to represent the barotropic component by comparing with the barotropic component estimated as the average on the vertical and the variations. And we found that this EOF 1, which is the barotropic component, is really dominating the signal, with the variance explained about higher than 90% for 4 of the 5 zones. And now we also noticed that the profile of the dominant EOF of EOF 1 is close to constant on the vertical on the shelf in zones 1 and 2, and that's consistent with the results from Lago et al. Further south along the South American coast. Now, but if we look at the zone 3, which is offshore of 400 meter depth, we see that EOF 1 is more equivalent barotropic, meaning that the velocity magnitude varies with depth while keeping the same direction here at the alongshore direction. And here in particular, we see that the velocity tends to go to 0 towards the bottom. And now we move to the data that we had access to along South Africa. So we had access to 3 moorings inshore of site Z. So those are the moorings M3, M4, and M7 that you see on the map here. So M7 is really close to the mooring Z, which is the most eastern one of the Samba area. And so similar to what we did for the data along South America, we rotated the velocity field into the alongshore and cross-shore directions, and that's a rotation of about 36 degrees following the 400-meter isobath overall direction. And we followed the same approach by looking at the currents under the Ekman layer, and then estimated the barotropic component as the average on the vertical, and the baroclinic as the total current minus the barotropic component. So those are the current rows for each of the moorings. So the coast is on the right and offshore is on the left. So the current is mainly northwestward and following the 36-degree direction. And that's following the direction of the Benguela current in this area. We also noticed the southeastward component in the offshore mooring here that we don't see as much in the inshore moorings. And as along South America, as the cross-shore component is small and will be neglected in the subsequent analysis. So here is the EOF decomposition of the alongshore current on the vertical. So EOF1 is in blue and EOF2 is in red. And for each of the mooring, the EOF1 represents is very highly correlated with the barotropic component. So it represents the barotropic component of the current. And we see that the EOF analysis shows that this mode 1 is really dominating the signal, and so the current structure is largely dominated by the barotropic mode. And we see upper on the shelf, the vertical mode is nearly constant on the vertical, but not so much when we go offshore. The profile tends to go towards 0. And yeah, I forgot to mention that M7 profile that don't go to the bottom because the ADCP was located halfway on the vertical of the mooring, because the bottom is closer to 1300 meters here. So we only have access to the upper part of the current profile. And so we then compared the data from altimetry with the PICE data like we did along South America using the CTOH altimetry data. And so here are where we did the comparison. So we found that the satellite altimetry data between site Z, between altimetry and the site Z dynamic height anomaly has a more limited correlation than between the site Y, which is the second next Samba mooring, and the coastal and the altimetry data, because as you see on the map, the mooring Y is very close to the satellite tracks. So that probably explains why the correlation is much better, with reaching almost 0.7. So we really see that at site Y, the altimetry data is really able to reproduce the variations that are observed in situ. And then we also estimated the geostrophic velocity between the moorings Y and Z that are the moorings of the most eastern ones of the Samba area. And so we compared the barotropic component of this geostrophic velocity between Y and Z with the first EOF mode of the decomposition of that velocity field. And we see on the left that those two time series are very highly correlated, meaning that the EOF1 really represents the barotropic component. And on the right, you see again the vertical profile of the two dominant EOFs, EOF1 and EOF2. And you see, so the mode 1 really dominates the EOF decomposition with 96%. So really the EOF1 is the main, explaining most of the current variability. And we also see that it's equivalent barotropic, because as it decreases towards 0 near the bottom. So to briefly summarize what we found in the analysis of the in situ data, we found that the current was essentially barotropic inshore of mooring A along South America, with inshore of 400-meter isobath, near constant current on the vertical, and offshore of that isobath, a more equivalent barotropic current that is going down to 0 near the bottom. On the eastern side, along South Africa, we found that the current is also mostly barotropic inshore of the Samba array, with at the most inshore mooring that we had access to for the ADCP, the current is near constant on the vertical, and further offshore it's more equivalent barotropic down to 0 near the bottom. And so we decided to consider the current as constant on the vertical between the coast and the 400-meter isobath, and equivalent barotropic down to 0 near the bottom beyond the 400-meter isobath. And that's the two schematics that I'm showing here. So on the left is the constant on the vertical in the upper part of the shelf, and down the shelf break on the right is the current decreasing to 0. And that allows us to project the surface current on the vertical. And so we were then able to estimate the transport. So we first added the mean dynamic topography from the most recent CNES dataset. So CNES is the French space agency. They are the ones deriving the mean dynamic topography fields for altimetry. So we added this MDT to the long track sea level anomaly to obtain the absolute dynamic topography, from which we estimated the absolute across track surface geostrophic current. And then we estimated the geostrophic transport on each side of the array by integrating this absolute across track surface geostrophic current, first vertically using the two profiles inshore and offshore of the 400-meter isobath that I just presented, and horizontally between the coast and the isobath of the most inshore mooring of the Samba array in order to close the line. And that's what we obtained. So that's the meridional transport inshore of mooring A. So that's the transport along South America, which is mostly southward, and that's the signature of the Brazil current. And it presents large variability and frequent reversals. On the eastern side along South Africa, the transport is mostly northward, and that's the signature of the Benguela current. And this time series has much smaller variability and fewer reversals. And if we add both time series, that's the total inshore geostrophic transport at 34.5 south that complements the Samba array. And we see that the mean transport by summing those two data sets is close to 0. And it's almost 0 Sverdrup, it's 0.03 Sverdrup. So, which is quite remarkable. But what we see also is that variability is non-negligible, because the temporal standard deviation is around 4 Sverdrup. And we also see that the total transport time series is highly correlated with the transport along South America. That's where most of the variability lies. And so to conclude, we found a way to estimate the meridional transport inshore of the Samba array using only observations, coastal altimetry data, and in situ data. The current observations suggest that the currents inshore of the array are mostly barotropic, and that's what allowed us to do these estimations, the transport estimations. And so this estimate lead to a mean meridional transport inshore of the Samba array that is close to 0. However, the variability is not negligible, because 4 Sverdrup is to compare to 15 Sverdrup in temporal standard deviation from the main Samba array. And so that's about 25%. So that's really non-negligible, and that's a component that should be monitored. And so the next steps of our study is to estimate the uncertainties in our transport quantification by using other altimetry data sets in sort of ensemble approach, in which we can, from which we can derive some uncertainties, and also explore the sensitivity of our results to the choice for the vertical projection. How sensitive our results are to those assumptions. We also need to add the Ekman transport, which is expected to be very small because it's a very small area, and like Lago et al. Did that calculation on the North Argentinian shelf, and they found less than 0.1 Sverdrup, something like that. And then we also want to extend the time series to include the JASN3 data that are posterior to 2016, and so that would allow us to complement this time series. And we have a manuscript in preparation to present these results. And that's all I have. And thank you very much for your attention.
Okay, great talk. Let's move on to the Q&A session. We have a question from Renalis. Have you looked at the whether the boundary current transport variation adds or subtracts to the MOC variation estimated without coastal altimetry?
I can clarify what I mean if you'd like.
Please.
Yeah, because
I was just the estimate that we get from the moorings is higher than any other method of estimating, and so we were wondering if I was curious if there's some compensation, if the variability that you see on the boundaries actually compensates for what is happening in the interior and might reduce the total variability if it's included.
Yeah, that's a good question. That we would need to look at the time series to see if they have to be related, because the Samba array really cuts the boundary current in half. So there is some the signal will be correlated. So yeah, that's a very good point, and that's something we can look at more closely on. I think it will be on each side, and then we can look at the total time series as well to see how they impact each other. Yeah. Thank you for the question.
Okay, a question from Rick. Have you examined whether the inshore Brazil current variation is correlated with what's happening on the western edge of the Samba array?
Yeah, that's
pretty much Renelis's question, really. Once I kind of heard her elaborate on it, is again the question of correlation because of the length scales that you would assume for those flows. So yeah, I guess that just occurred to us at the same time.
Yeah, it's a very valid point. That would be interesting. They have to be related, because they are the coastal altimetry on each side, they cut into the same vein, same current system as the edges of the Samba array. So yeah, there has to be correlation, and it would be interesting to see what is missed by one and by the other, depending on the location of the current. That's a good question. That would be very interesting to look at.
And when we've done that comparison with some models with people that we collaborate with, I mean, it looks like that's what's happening in models, but the question is that happening in the real ocean?
Yeah, exactly. If that's something that we can use observations to address that'd be great. So yeah, that's a very good suggestion.
Any more questions? Well, maybe I do have a question. So Matthieu, what explains the barotropic nature of the current inshore from the array? I would expect the other way around, closer to the coastline, it would be more baroclinic.
So I think, yeah, I mean, I was expecting more barotropic signals, so I was not that surprised. But yeah, the signature, the impact of the wind on the shelf. It's a wide shelf, so I guess there's the little impact of the deeper circulation on the shelf. It doesn't impact the shelf as much. When the fact that the barotropic signature extends offshore of the shelf surprised me more, and we believe that it's maybe because we captures the upper part of the Brazil current or Benguela current that extend to about the location, at least on the Benguela side, that extend vertically down to about the location of the most inshore moorings. So what appears like a barotropic signature is maybe because we measure only the upper part of a baroclinic current system, but that extends further deeper than what we measure. So that's a possibility.
Okay, thank you. Marlos has a question. Have you looked at the spectral variability of this time series?
No, we haven't looked at we haven't looked at that yet, but that would be interesting. They will be dominated by the surface from the altimetry, but yeah, that's something we need that would be interesting to add. And then yeah, if we do that after adding the JSON3 data, we'll have a longer time series, so that would be even more robust to do. But yeah, it's a good point.
Any more questions, guys? It looks like we don't have any more questions. So thank you, Matthieu, and thank you everyone for joining the seminar. And until next time.
Yeah, thank you everyone. Have a good day.